And what I'd like to do now is just prove it so we get it actually correct. So let's suppose f tilde of s is continuous for all s between 0 and infinity. So it has to be continuous. Then the limit as s goes to 0 of s f tilde of s is equal to the limit as t goes to infinity of f of t. Now, that's kind of cool because remember when we introduced the Laplace transforms, we said that wonderful. We saw that the Laplace transform has some nice properties. One is that when we take the Laplace transform of derivatives, the derivatives disappear and we get something that's algebraic. Similarly with integrals, we get things that are algebraic. So we can turn an equation that has derivatives and integrals in it into one that's just algebraic. It's much easier to solve. The only problem is we solve for f tilde, not for f. And obviously, here in the real world, we want the answer f of t. We don't want f tilde of s. F tilde of s is very nice, but it doesn't answer my problem. I want to know what's going to happen in time, not in some funny variable s. So we said that typically we have to invert the Laplace transform, and we said we would do it using the table in this class to try to go from f tilde of s to f of t, which is what we really want. The nice thing about the final value theorem, as well as a few other things we're going to come up with in this class and the next class, is that many times you could get all the information you want without inverting. You might say, that's amazing. Well, you have to remember, what do you usually want to know in a problem? Let's say you're interested in Ca of t, in the concentration of A coming out of a reactor. Do you really want to know, I mean, it would be nice, but do you really need to know Ca at every instant of time? Or do you really just want to know what will the system blow up, or will it be not blow up? What will the new steady state be? Will there be a new steady state, or will things go to hell? A lot of times that's enough to know that. You also might want to know, will the solution oscillate, or will it just go exponentially to where it's going? So those are the kinds of questions you often want to ask. So it's always good to know the question before you look for an answer. And many times you can get the answers directly from f tilde without having to do the inversion. If you need more information, you can do the inversion. And the final value theorem is one way that will help you. So for example, if the reactor is going to blow up, then there won't be a limit as t goes to infinity. That is, f will go to infinity. So I should be able to see that from the left side of this equation, that the limit of s, f tilde of s, would go to 0 as s goes to 0. I don't even have to invert it to know that I'm up the creek, that things are going bad. On the other hand, if I go to a new steady state, well, I can determine that steady state by this limit if it's finite. And we looked at that case for the 1 and 2 CSVRs in series last time in the last nanosecond of the class. So let's just prove this because it's easy. Because it's always good to not take everything at my word, but to actually look for a proof. So let's recall that from this equation right here, that the integral df dt from 0 to infinity of e to the minus st dt, we said that this thing was equal to s f tilde of s minus f0. Again, the tilde means I transformed it, so it's a function of s. No tilde means it's still a function of time. Let's just integrate this thing by parts. No, actually, I want to take the limit. Let's do this one thing at a time. I would like to take the limit as s goes to 0. Yeah, so let's now take the limit as s goes to 0 both sides. Well, on the left-hand side, again, the integral itself is a limit, because you had in calculus as a Riemann sum. So what I'm going to do, because we're engineers, is I'm going to switch the limits. I'm going to move this limit inside. I can't necessarily always do that. Remember, I told you, in mathematics, you have to prove that you're allowed, when you do that, you don't change the answer. So that one, I guess you're going to have to believe me, that on this one, you can prove it, but I'm not going to prove that in great detail. So I'm going to move this in, and I have the integral from 0 to infinity, the limit as s goes to 0 of df dt, e to the minus s t dt. F doesn't depend on s. The only s I see here is e to the minus st. So what's the limit as s goes to 0 of e to the minus st? 1. So this thing just becomes 1. And now I just have the integral of the derivative. What is it from the fundamental theorem of calculus? What is the integral of a derivative? I can't hear you. Cancels out. What does that mean in English?
The original function.
The original function. So this just becomes f limit as t goes to infinity of f of t minus f of 0. So if we believe this is equal, that says this equals this. The f of zeros cancel, and I have the limit as s goes to 0 of this is equal to the limit as t goes to infinity of this. So it's proved. Yep.
Where'd you get the limit as t goes to infinity?
Where did I get the limit? Because the upper limit is infinity. So I don't like to write f of infinity, because f of infinity might not exist. So I write it as the limit as f goes to infinity. So really, I could have written this, the limit, this goes to, I don't know, q, and the limit is q goes to infinity here. Any other questions? Okay, so as we saw last time, actually, do I want to do one more theorem before? Yeah. So let's do a simple example. Notice I said that f of s has to be continuous. If f of s weren't continuous, then I might have a problem here. So let's look at a counterexample when f is not continuous. Example when f tilde of s not continuous. And that way you'll see that this supposition was important. So let's let f tilde of s equal to k over s 1 minus st. Is that the one example I want to use? St minus 1. Okay, not a big difference. And now you can notice here that, okay, I only require it to be continuous for s greater than 0, less than infinity. So obviously this has a problem at 0 when s is 0, but I don't care about that because this is not a less than, or greater than or equal to, it's a greater than. But notice over here, when s is equal to 1 over t, positive. When s is 1 over t, I get 1 minus 1 is 0, and this blows up. If it blows up, it's not continuous. This is going to infinity. So, in fact, it goes to plus infinity from one side and minus infinity from the other side. Is that right? This goes to 1. No, it just goes to plus infinity. So it's as we said, it's discontinuous. So let's examine this and this and see if they're different. So note the limit, let's look at the limit as s goes to 0 of s f tilde of s. Well, if I do that, I get the limit as s goes to 0 of k over st minus 1. S is 0, so I just get minus k. On the other hand, let's invert this. So if I invert this, and I find f tilde of t, f of t. So I go to my sheet. Has everyone gotten one of these sheets? People have been trickling in. So just pick them up. I don't have to hand them out. Okay, so ST minus 1. So notice that I have in the table on line 4, I have 1 over 1 plus S tau, and what to do with it. So I want to get this in that form. So 1 over ST minus 1, I want to get it in this form. So I'm going to multiply top and bottom by minus 1 over t. So if I do that, I have a minus 1 over t up here. Actually, minus 1, no, actually just minus 1. So I get a minus 1 on the top, and here I get a 1 minus st. But I could write this as plus s times minus t. So now I've gotten it in the right form. Once I have it in the right form, now I can invert this. So I notice that what I have here is 1 over s, so I can bring the s down here. And I have a k up there. K, k, k. And now I can invert this. So that tells me that f of t, if this is f tilde of s, f of t, the minus k comes along for the ride. And I have s over 1 plus st. So there I really should be looking at line 5, not line 4, line 5. So for line 5, for a is equal to 0, I should get 1, a is 0, minus e to the minus t over the thing multiplying s. But the thing multiplying s is minus t. So those cancel, and I get 1 minus t over t, little t over big T. Let's bring the minus signs in. I've got k times minus 1 plus e to the t over big T. And what happens as t goes to infinity to this? What happens to e to the little t over big T as little t goes to infinity? Somebody loud? Goes to infinity. So notice, if I look at limit of s, f tilde of s, as s goes to 0, I get minus k. But if I take the limit as t goes to infinity of f of t, I get infinity. They're not the same. Now, does that mean the theorem's wrong? No, because the theorem supposes that f tilde is continuous. And here's an example where it's not continuous. Yep.
In your exponent, the second to last line, are those pluses?
Yes.
Plus t, plus t?
Yes. They were 2 minuses, and I canceled them. Maybe I should leave them as 2 minuses. And then they cancel and become little t over t. Other questions? All right, so let's look at the next theorem, which is the initial value theorem. And the initial value theorem says limit as s goes to infinity of s f tilde of s is the limit as t goes to 0 of f of t. So notice what we're finding here is a duality, that when t goes to infinity, that's like s going to 0, sort of. When t goes to 0, that's like s going to infinity. So s and t are dual variables. They're like partners. And let's just prove this. Again, let's start from here. But now I'm going to take the limit as s goes to infinity.
Does it not have to be continuous in this case?
No, because I'm taking the limit, well, apparently not. We'll see if I use it in the proof. Integral from 0 to infinity, df dt, e to the minus st. dt is equal to S f tilde of S minus f of 0. Now I'm going to do the same thing. I'm going to switch the limits of the integral when the limit as s goes to infinity. And I'm going to claim that that's legal. And I have the limit as s goes to infinity of df dt, e to the minus s t dt. And the only s in here is in the exponential. What's the limit as s goes to 0, s goes to infinity of e to the minus st? Come on, you can do this. 0. When s goes to infinity, this is e to the minus infinity is 0, so this is 0. And if these are equal, then that tells me that therefore the limit as s goes to infinity of s f tilde of s minus f of 0 is 0. So it's just f of 0. Now, usually we know the initial condition. So it's not necessarily that super useful, because typically when you have a problem, you know the initial condition. So there's no mystery to see what the initial condition is. But it's still nice to know, and you can imagine there might be some situations where you have to back it out. Why don't we do one little example where we can apply these? Okay, so we did, I noticed the application a little last time. If you remember, we had, notice how I strategically erased everything that I didn't need today, but I left some stuff on the blackboard. For a CSTR, a single CSTR, we saw that the solution for step change in Cn was equal to this guy here. So if I apply the final value theorem, so I want to know what the steady state is later on, I multiply by s, this cancels, and I take the limit as s goes to 0, and this just becomes 1. So I'm just left with delta Can over 1 plus kt. And that's exactly right. That is, in fact, the steady state value. For the case of 2 CSTRs in series, again, here's the solution. Here's where they're of different volumes. When I multiply by s, this cancels. I set s equal to 0, that becomes 1, that becomes 1, and I'm just left with delta Can times 1 over kt tau 1, 1 over k tau 2, which is exactly the steady state for 2 CSTRs in series. So, and of course, if I want the initial condition, I take the limit as s goes to infinity. If I take the limit as s goes to infinity of s times this, the s cancels, and as s goes to infinity, the denominator goes to infinity, so this goes to 0. That is, the initial condition of Ca prime is 0. Well, duh, that's why I constructed Ca prime. So it would, so its initial condition would be 0, because any prime variable is its value at t minus its value at 0. So at 0, it's something minus itself at 0. Similarly here, as s goes to infinity, I multiply by s, this cancels out, but as s goes to infinity, each of these goes to infinity, and the whole right side goes to 0, and I'm left with Ca2 prime is equal to 0. So far everything is consistent. Miracle. Why don't we do one more example? Let's do our tank example, because this is a tank with jump. So I've got V in, I've got V out, and I've got L of T, and I've got a cross-sectional area A. And we've looked at this before, we did a balance. And the idea here is V in goes from a value of t less than 0 to a value of t greater than 0. So this is all review. You have the setup of this problem we've done before. So that we're given that V out is equal to k square root of L. So as L changes, V out changes. And when we linearize, which we did already, we said this is equal to the square root of L at t less than 0 plus 1 over 2 square roots of L of t less than 0 times L minus L of t less than 0. So that we already did last time, plus the remainder, which we neglect when we're linearizing. So this you all have in your notes. In fact, everything I'm going to do now for the next few lines, you already have in your notes. So when we do the balance, so solution, we do the balance, and we do the unsteady state balance. We have A times the L dt, the change in volume, is equal to V in minus V out. Well, that's pretty straightforward. So let's write that we notice that this is equal to V in minus the linearization. So I'll always make this approximately equal to A square root of L t less than 0 minus K times over 2 square root of L t less than 0 times, this is L minus L of t less than 0. I can just call that L prime. This thing is just an L prime. And now what I'm going to do, I'm going to divide through by A. Now we have to cancel the A here. And now this is the unsteady balance. Now I'm going to take, so this is the way you do a problem. You do the unsteady balance. If you need to linearize, linearize it. Now we do the steady state balance for t less than 0. If for t less than 0 the system was at steady state, if it was at steady state, we do a steady state balance. Well, in that case, this is dl t less than 0 dt. Well, it was steady state, so I said equal to 0. That was equal to v in for t less than 0 over a minus v out, but v out we know was minus k over a, the square root of L for t less than 0. I don't even have to linearize that, or if I want to linearize it, I can, but L prime for t less than 0 was 0. So I just take this term anyway. And now what I do is I subtract. Again, I've done this for the CSTR, 1 CSTR, 2 CSTRs, etc. Yes? Well, can you take your message? I'm subtracting because remember my goal is to get variables, a dependent variable whose initial condition is 0. So I'm subtracting so that on the left I'm going to get dl prime dt is 0 because L prime of 0 is 0. And that makes all the algebra much easier. So that is exactly the reason why I'm doing it. I'm doing it to get to prime variables as opposed to unprime variables because if you remember when we did, before we started doing Laplace transforms, we did the first order linear differential equations and we had one term that depended on the initial condition and then another term that didn't. So by making L prime, working with L prime, that first term was 0. So if the solution is simpler in one method, it's going to be simpler in the other method as well. It's always good, always very important to ask why I'm doing something. So almost, it's as important to know why I'm doing something as to understand the details. So it's very important you ask that question. Thank you. Other questions? Okay, so here I have dl prime dt. And what I have here is this is v in prime over a. Move that prime closer. Because it's v in a t minus t less than 0. And notice this and this term are exactly the same, so they cancel. And here I have minus k over 2 root L of t less than 0, a times L prime. And notice I can rewrite this as the L prime dt plus L prime over t is equal to V in prime over A, where this thing is 1 over t. So the time constant here is 2 root L with t less than 0 A over k. That's the time constant. And this is exactly of our favorite form. In the old days, meaning a week ago, we would have just appealed to the equation that I had up here for 2 weeks. But we're going to do this with Laplace transforms. So if we do it with Laplace transforms, I take the Laplace transform of what I just erased, but we've seen it so many times we know it by heart. This is L prime of S minus L prime of 0. And this is again the answer to your question. This thing is 0 because we're in L prime, So this is 0. That's the Laplace transform of this. Plus L prime over t is equal to V in prime over A. I want you to notice something before I add a tilde, V in prime tilde. Okay, so I want to notice something before I just go on. Notice when I write it in this form, I've got the dependent variable L prime on the left, and on the right I have the forcing function. Why do I call it the forcing function? I call it the forcing function because it's because this change in V in prime that's driving the problem. The tank was very happy for t less than 0 at a fixed height. It was very happy. There was no problem then. All of a sudden we changed V in. So the change in V in is driving the change in L prime. So that's sort of a way of looking at this problem. And now we can go through and try to solve this. So this is L prime tilde. L prime tilde times S plus 1 over t. Well, S plus 1 over t is 1 plus st over t. Is equal to V in prime tilde over A. Or L prime tilde is equal to t over A times V in prime tilde over 1 plus st. And now, until now, we've only looked at step changes. Let's look at a step change. So if V in prime, as we saw last time, when we go to prime variables, V in prime tilde is just delta V in times divided by S. Because V in prime is delta V in times theta, the step function. Yes? I'm sorry, you have to take the mass.
What did you set S as?
Okay, I have S here, S plus 1 over t. When I bring S, bring that under one denominator, I have to multiply and divide S by t. So I get an st in the numerator and t in the denominator. So if you break this up, this is 1 over t plus S. And again, this is V in prime is just delta V in times theta of t. So therefore, V in prime is delta V in over S. So if we go through, we have, so therefore, L prime of t is t over A times delta V in divided by S 1 plus st. And, yes? Question? Okay, so let's notice that that's again line 5. If I invert, I go to line 5. And I have L prime of t is equal to t over A delta V in. And for S 1 over st, again in line 5, that just gives me 1 minus e to the minus t over t. So notice I have a time constant here, and here I have my solution. And let's just, again, check the condition in infinity, the final value theorem. The final value theorem, the limit as t goes to infinity of L prime of t. Well, as t goes to infinity, this just becomes 0 and get 1. I have t over a delta v in. So let's just notice that if I look at L prime of t, the limit as t goes to infinity. So this is the change in the output over the change in the input. That's what we call the steady state gain. And that's equal to t over a. So we have an example of that. And let's just make sure that I get the same answer, that this is the limit as s goes to 0 of s f tilde of s. Well, here's s L prime tilde of s. If I multiply by s, that goes out. And now when I take the limit as s goes to 0, that goes out. So I just get t over a delta v in. That's exactly what I got. How about at 0? What happens in the initial value theorem? The initial value theorem says I multiply by s, and I take the limit as s goes to infinity. When s goes to infinity, the denominator blows up, and I'm left with 0. Well, L prime of 0 is 0. So both of those theorems obviously hold. However, since we have the solution in terms of delta v in, or in terms of v in prime, why don't we say, what if we choose a different v in prime? What if v in looks like this? Here's 0, it's a steady state, it goes off. I have a finite amount that I put in 0, and then it goes back to where it was. So let's imagine that I have a constant flow rate, then all of a sudden someone dumps a bucket of fluid in and t is equal to 0, but the flow rate hasn't really changed, v in. So what happens then? Well, normally it takes a finite amount of time to dump a bucket of fluid in. But let's say I could do it really fast. Really fast means fast compared with t. Fast compared with t. So then this looks like a delta distribution. So in that case, so then v in prime is just equal to some number, an amount, the volume of the bucket, v bucket, times delta of t. Well, then I can still use this formula because I have v in prime tilde is v bucket times the Laplace transform of delta. And if you look at your table, which everyone should have now, since it was on, I made enough copies for everyone, that's just 1 times 1. So therefore, L prime tilde in this case is equal to t over a times v of the bucket over 1 plus st. And now I have 1 fewer s than I had here. So now I go to line 4, not line 5. And in line 4, we have 1 over 1. So the constants come along for the ride. L prime of v is equal to t over a, v bucket, times 1 over st, 1 over 1 plus st, but that just gives me 1 over t times e to the minus t over t. T's cancel. And that's my time-dependent solution. Instead of a 1 minus an exponential, I just have the exponential. Let's see what happens as t goes to infinity. Well, what happens to the exponential as t goes to infinity? Goes to 0. So I just get 0. So that says that the height of the tank goes up initially, but then it comes right back down. It was a certain value. At t equals 0, it went up. And then it exponentially decayed back to where it was. Well, and let's just make sure that this is, the limit is s times L prime tilde of T. Well, if I multiply by S, this, V in prime tilde, here we go. I multiply by S, and I take the limit as S goes to 0. The numerator goes to 0, the denominator goes to 1. This goes to 0. I have 0 over 1. So this is correct. And of course, the initial value theorem is the limit as S goes to infinity. As S goes to infinity, this is also 0. So they perfectly agree. Yes?
Would we be allowed to use them now without proving them?
Yes, of course. You prove a theorem once, you don't prove it every time. It's a tool. Now that you know it works, use it. Not only you're allowed to, you should use it. We proved it. Once it's proved, it's proved. Any questions? Questions? Okay, so now we're ready for new math. Not the new math in elementary school, but new math. So I'm going to erase some of this. Now, why do I call this new math? It's not really new. It's just put together in a way that's new, that you haven't seen before. Remember, we said we take problems in the time domain, and then we move them by Laplace transform into the S domain, this funny S domain. And if we want to know the full time dependence, we have to go back to the time domain. There are many questions we can answer without going back to the time domain. But when we go back to the time domain, we're using this table or a better one. Instead of that's 1 page, maybe that's 5 pages. But obviously, you can't put every possible function in here that you'll ever come up with. So, and you don't want to do that, because some functions you can break up into a sum of simpler functions. So whenever you can do that, you don't put it in the table. You only put the irreducible functions, the ones you can't break up anymore in the table. So what we're going to look at is how we break up more complicated functions into simpler functions. So, and that's called partial fractions. And usually you have a very simple example of this in your kinetics class. So let's do a simple example, and then we'll do it more generally. So if I have f of s is 1 over s minus a, s minus b. So that's one you may have had in your kinetics class. That's usually the one that comes up in elementary kinetics. So what do? If I ever have to integrate something like this, I write it as some unknown constant a over s minus a plus b over s minus b. And I want this to hold for all values of s, not just one. So I want to solve for the constants a and b. Hopefully I can do that. So the way I solve for it is I multiply through by the denominator. And I have 1 is equal to a times s minus b plus b times s minus a. So I multiply through by s minus a, s minus b. And then what I do, since I want this to be true for all s's, not just for a particular s, is I equate the coefficients of each power of s on both sides of the equation. So if I look at s to the 0, I have 1 on the left, and here I have minus ab, and then here I have minus ba. That's the on the right side of the equation, the s to the 0. And s to the first power, I have 0 on the left, and here I have a plus b. Because I have a times s and b times s. So this tells me b is equal to minus a. And then I can plug in here b is minus a. So this thing becomes plus a. And I have a times a minus b. And that tells me a is equal to 1 over a minus b, and b is minus 1 over a minus b. And I have f tilde of s is equal to 1 over a minus b times 1 over s minus a minus 1 over s minus b. So you've seen that before, I hope, even though, so I did it in lightning speed, but because I believe you've seen it before. Is that correct? Otherwise, it's basic algebra. Now, we'd like to do this for more complicated situations. In particular, very often in this class, and in many other classes, we'll find f of s, f tilde of s, is a ratio of polynomials. So I may have some numerator, n tilde of s, over d tilde of s, where n tilde of s is some polynomial, and d tilde of s are polynomials in S. And we know you can factor polynomials. So let's figure out what we can do if we can factor the polynomial. So let's assume that d tilde of s can be factored. Or let's factor it. If it's a polynomial, we factor it. It's not an assumption. We know we can factor it. And I can write this as s minus alpha 1, s minus alpha 2, dot dot dot, s minus alpha n. Where alpha 1, alpha 2, dot dot dot, alpha n are the roots of the polynomial. And I'm going to look at three cases. So we're going to look at three cases of how to handle this. Case 1. All the alphas are distinct. Alphas, real and distinct. Case 2. Some alphas are the same. But they're still real. And case 3 is we have complex alphas. So those are the three cases we're going to look at. And let's see how far we get today if we actually get to all of them. Not sure. But you know, I could talk even faster and then we'll get to finish the semester. Just kidding. Again, if I'm talking too fast, if there's something you don't catch, stop me. By the way, the reason for coming to class is not just to humor the registrar. The reason for coming to class is because there are certain new concepts that it's a lot easier to learn if they're explained to you, and if at that instant you can ask a question. Otherwise, you could just watch the video or read the textbook. Watching the video, you'll get it explained to you, but you can't say, stop, I don't understand that. And that you can do in class. So my hope is that coming to class is not a chore that you feel you have to do, but something you want to do because it makes it easier for you to learn. That's my goal. I'm not sure if I'll accomplish that, but that's the goal. Is I want you to feel that at any point, if there's something you don't understand, you can say, stop, I want that explained to me. That's why you're here. Okay, so let's start out with case 1. They're all the alphas are distinct. If they're all distinct, then I can write f tilde of s as n tilde of s over d tilde of s. I can write this as some m tilde of s over s minus alpha 1 plus some remainder of s, where the remainder does not have any roots, so where r tilde of alpha 1 is finite. R tilde of alpha 1 exists because there are no powers of s minus alpha 1 in its denominator. And the numerator is a polynomial. So I claim I can write this, and I just don't want to leave anything out. Actually, I shouldn't have the remainder here. I'll have the remainder in the next one. Is equal to c plus r tilde, c over s minus alpha 1 plus r tilde of s. So that's the claim. I need to prove that to you. So I can, since d has one of the factors of s minus alpha 1, everything else in m is n over all the other factors of d. So n m tilde of s is just n tilde of s divided by s minus alpha 2 dot 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 s minus alpha n. Because I just pulled out this one factor. So this is exact. I don't need a remainder, but I claim I could write this as a constant. It's called C1 plus R tilde of S. So let's prove that. So to prove that, let's multiply through by S minus alpha 1. If I multiply through by S minus alpha 1, I have M tilde of S is equal to C1 plus R tilde of S minus alpha 1. And now what I'm going to do is I'm going to take the limit as S goes to alpha 1 of this. Yep. S minus alpha 1. Alpha 1. This is alpha n. Yes. Yes. My bad handwriting. The two subjects I flunked in elementary school were penmanship and conduct. Okay, so let's take this limit. So here I just get m tilde of alpha 1, which should exist because there's no alpha 1 in the s minus alpha 1 in the denominator. And that's equal to C1. R tilde of alpha 1 exists. It's a number. S minus alpha 1 is 0. So I have m tilde of alpha 1 is just C1. So I know what C1 is. And I can write it in this way. So you can imagine, now I can go through and do the same thing for R tilde. I can write R tilde as some m2 over S minus alpha 2, etc. So in the end, I can write F tilde of S as m1 tilde of alpha 1 over S minus alpha 1 plus m tilde 2 of alpha 2 over S minus alpha 2 plus dot 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 plus m tilde n alpha n over S minus alpha n. And I might have some constant left over, which I'm not going to worry about. Actually, now I can invert this because each one of these has a 1 over S minus alpha. Now, of course, I have in the denominator, in the table, I have things that look like 1 over 1 plus ST. So let's just manipulate this. So I have an aside. Aside of broken chalk. Aside. 1 over S minus alpha. I'm going to multiply top and bottom by minus 1 over alpha. And if I do that in the numerator, I get minus 1 over alpha. And in the denominator, alpha times minus 1 over alpha is 1. And S times minus 1 over alpha is plus S times minus 1 over alpha. And notice, this is now of the right form. Because in the table, I have things that look like 1 plus ST in the denominator. And notice that my time constants, my T is minus 1 over alpha. So when I start with something that looks like this, it gives me a time constant that looks like this. So let's invert this. So this is still part of the aside. Continue. If F tilde of S is equal to 1 over S minus alpha, then F of T is equal to, well, what is it? Line 4. Line 4. Okay, so I have minus 1 over alpha. That comes along for the ride. And now I have 1 over t from line 4. 1 over t is minus 1 over alpha. Times e to the minus big T? Well, big T is this. In other words, f of t is equal to, these cancel, e to the t alpha t. So if f tilde is 1 over s minus alpha, then f of t is e to the alpha t. So what does that tell me? That tells me I can invert this. So now the aside's over, and this tells me that f of t from here is just equal to the sum I equals 1 to n of m tilde of alpha I times e to the alpha I t. I've done the inversion. Now, one thing let's notice before I go on. I've done case 1. Done. Let's just look at alpha I. What if alpha I, nothing here required alpha to be real. So I don't even need alpha to be real. Let's look what happens if alpha is negative. Let's say alpha is negative or is complex with a negative real part. So let's let alpha I equal to AI plus, maybe I shouldn't use I, let's use J, plus I times Bj, where I is the square root of -1. If A is negative, if this is less than 0, then I have a decaying exponential. We'll talk about e to the IB later. But as long as A is negative, I have a decaying exponential, and everything is going to go to steady state. So if all the AIs are negative, then I'm going to go to steady state, a new steady state. On the other hand, if one of the AIs is positive, if even one is positive, that's going to grow to infinity, and bad news. So that's called unstable. We'll talk in more detail about this when we do case 3. And you can imagine that if some of the A's are 0, if some of the A's are 0, then I'll only have imaginary exponents, and we'll need to talk about that when we get to it. Questions? Do we have a picture of this board? Or less than 0, go to a new steady state. I left out the 2. Sorry. Thank you. I wasn't writing fast as thinking. Okay, so let's go to case 2. In case 2, we're looking at a situation where a bunch of these are the same. So let's assume that n plus 1 of them are the same. So let's assume that f tilde of s, which is n tilde of s over d tilde of s, is equal to n tilde of s over s minus alpha to the n plus 1. So some number n, integer n, where n is of course 0 or higher. I claim that I can write this, let me just make sure I didn't leave anything out. I claim that f tilde of s can be written as Cn plus 1 over s minus alpha to the n plus 1, plus Cn over s minus alpha to the n, plus dot dot dot, plus C1 over s minus alpha, plus a remainder. Where again, the remainder term, where r tilde of alpha is exists. That is finite. So that's the claim. So when I have an n plus 1 up here, and I'll, just as I did there, here I came up with an expression for C1, I'll come up with expression for all of these guys. And let's prove them. So prove. Again, we'll do the same thing. Let's multiply by s minus alpha to the n plus 1. So if I multiply by s minus alpha to the n plus 1, I have m tilde of s. So this equal to this is equal to Cn plus 1 plus Cn over s times s minus alpha plus Cn minus 1 times s minus alpha squared plus dot 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 plus C2 s minus alpha to the n plus C1 s minus alpha. No, this is n minus 1 and this is to the n. Okay, and first, so let's notice that m tilde of alpha, well, when I say equal to alpha, all of these terms go to 0. And of course, I have r tilde of s minus alpha to the n plus 1. Well, at alpha, r tilde of alpha exists, is just a constant. So this becomes 0, 0, 0, 0, 0. This is Cn plus 1. Okay, that's great. That was the easy part. That one worked like the first case 1. Let's do the next one. Let's take the derivative. dm tilde ds is equal to, the derivative of this is 0. Here I have Cn plus Cn minus 1 s minus alpha times 2 plus dot 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 plus C2 times n minus 1. S minus alpha to the n minus 2 plus nc1 s minus alpha to the n minus 1 plus n plus the derivative of this thing. The derivative of this is r tilde prime s minus alpha to the n plus 1 plus r tilde times n plus 1 s minus alpha to the n. So like this, I took the derivative. And now let's set alpha equals 0, s equals to alpha. When s is equal to alpha, this is gone, this is gone, this is gone, this is gone, this is gone. So all I have left is Cn. So I have a value for Cn. I have that. Let's take the second derivative. Questions? Let's take the second derivative. D squared m ds squared. I take the derivative of this, Cn is gone. So I'm left with 2 times 1 times Cn minus 1 plus dot 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 plus n minus 2, n minus 1, n minus 2, C2 s minus alpha to the n minus 3 plus n minus 1, C1 to the s minus alpha to the n minus 2. Plus the derivative here, which is r double prime s minus alpha n plus 1 plus r prime times n plus 1 n s minus alpha to the n minus 1 plus r tilde times n plus 1, let's see. I need to take the derivative. Actually, I think I have everything. I took the derivative of this one and now let's take the derivative, evaluate this at s equals alpha. At s equal alpha, this is gone, this is gone, this is gone, and this is gone. So all I'm left with is this is equal to Cn minus 1 is equal to dm tilde ds squared at s equals alpha divided by 1 over 2 factorial. Because taking two derivatives gave me a 2 times 1, which is a 2 factorial. If I go to the next one, I'll have a next derivative, I'll have 3 times 2 times 1 times Cn minus 2. So I think you can see, if I continue with this, that Cn minus m is equal to some derivative of m tilde ds to some power. So when it was n minus 1, I had 2 of them. When it was n minus 0, I had 1 of them. So it was m plus 1 derivatives, n plus 1. And divide it at s equals alpha times 1 over n factorial, m plus 1 factorial. So now I've shown that this can actually be written in this form, and I've given you a formula for each of the c's. So we have a formula for each of the c's, Cn plus 1, Cn, and in general, maybe I shouldn't use m because m is up there. So let's call it P. I don't want the m to be confusing, so I use the capital M. So Cn minus P, and this is of course, just let me finish the sentence. This is of course from P equals 0 all the way up to n minus 1. Yep.
What is M?
M is this guy. M is n tilde over d tilde with the factor s minus alpha over n plus 1 pulled out. It's everything else. It's all of the numerator minus the denominator. I'm sorry, divided by the denominator, all the factors of the denominator except the ones s minus alpha. And I've assumed that if there were any common factors, they would cancel. So there are no common factors. Other questions? Okay, so now I need to know, how do I invert these guys? I know how to invert this guy, but I don't know how to invert those guys. So let's look at the table. If I look at the table on line 6, it will tell me how to do it. So line 6 in the table will tell me what I need to know. Line 6 has a 1 over 1 plus s tau to the nth power. So I just need to know how to get this in the right form. We already know that 1 over s minus alpha can be rewritten as, I already did that algebra, as minus 1 over alpha over 1 plus s times minus 1 over alpha. So obviously, this thing to the nth power is equal to this thing to the nth power. So if f tilde of s is 1 over s minus alpha to the n, then f of t from line 6, well, the minus, this is equal to minus 1 over alpha to the nth power. That comes along for the ride. And now the denominator is just in this form. So let's see what the denominator, what that tells me. That's line 6. So everyone has their sheet, I hope. Line 6, we've got 1 over t, and here again, t is minus 1 over alpha. So I have 1 over tau to the n. So 1 over tau to the n is 1 over minus 1 over alpha to the n. And then I've got t to the n minus 1 times e to the minus t over t. E to the minus little t over big T. The minus is canceled, so e to the plus alpha t. Same as what we did before, divided by n minus 1 factorial. And notice again, this cancels. So notice, what do we get here? What we get here is, okay, we have the factorial, but we have the exponential. Well, we had exponentials before. Exponentials are no surprise. We had exponentials. But now we have powers of t times exponentials. Now you might say, so what? It's just a simple function. Well, remember, we had that before. When we did two CSTRs in series, if the volumes were the same, you should be listening, not writing them. If the volumes were the same, if you remember, we had terms t times an exponential. We didn't have that when the volumes were different. Well, what happens when the volumes are the same? When the volumes are the same, I had in the denominator 1 plus st1 times 1 plus st2. When the volumes are the same, t1 and t2 are the same, so I get a 1 plus st squared. That's exactly 2 powers, that's exactly case 2. When I have two CSTRs in series that have the same volume, I get a 1 plus st quantity squared in the denominator. So therefore, and is 2 there, I get a term that's t e to the alpha t. It's exactly consistent with what we had before. And of course, it's divided by 1 factorial. What if I have 3 CSTRs in series? And if they're all the same size? Then I'll have a 1 plus st cubed in the denominator. If I have a 1 plus st cubed in the denominator, so that's a case where n is equal to 2, that means I'll have a term that's just an exponential. I'll have a term that's t times an exponential. And I'll even have a term that's t squared times an exponential. And we call that a case of resonance. And it behaves qualitatively different. If I have something that decays exponentially, when I multiply by t, so notice if I just look at e to the alpha t for alpha negative, and that looks like this. If I have e to the alpha t for alpha negative, that looks very different. It looks like this. It looks very different. So we want to keep in mind that multiple roots change the character of the solution. And we call that a resonant condition. Are there any questions on that? Questions? Okay. Well, that brings us to the interesting case, or the most interesting case, which is the case of complex roots. Case 3. Now, if the physical problem has real coefficients, so if the physical problem, meaning what gives us n tilde as n d tilde, if the physical problem is physical, then all the coefficients of these polynomials are real. Now, as you know from quadratic, solution of quadratic, you can have a quadratic equation where the coefficients are real, but the roots are complex. No big deal. When the square root b squared minus 4ac, if b squared is bigger than 4ac, if b squared is less than 4ac, then I get complex roots. But if you remember from the solution of quadratic, you don't get arbitrary complex roots, you get complex conjugates. You get minus b plus or minus the square root of b squared minus 4ac. So if b squared is less than 4ac, you've got minus b plus I times something, and minus b minus I times that same thing. And that's because when you multiply them together, s minus alpha 1 times s minus alpha 2, you have to get real coefficients, because that's where you started. It's similar for more complicated, for any polynomial. So, in case 3, as long as the coefficients in n tilde and d tilde are real. And actually all I care about here is d tilde. Because that's the one that we're taking the roots of. Then all complex roots of d tilde come in complex conjugate pairs. A plus or minus IB. So if one root is A plus IB, there's another root that's A minus IB. They come in pairs. So that way when I multiply all these things together, S minus alpha 1, I erased it. No, when I multiply all these together, I'll get something with real coefficients. Now that is something that you prove in a number theory class. But it's an extension of what we know about quadratic equations. I notice that it looks like I'm at the end of the hour, so I don't want to go beyond that. We're going to go through this in great detail next time. And there's all sorts of neat things involved. Let me just give you one neat thing that we're going to need next time. If you remember, we said that e to the, so this is just an aside, because I don't have time to do a real derivation. I only have like a minute left. E to the I theta, we said is equal to cosine theta plus I sine theta. So if I take e to the minus I theta, I replace theta with minus theta. Since the cosine is an even function, the cosine of minus theta is the same thing as the cosine of theta. It's just as the cosine of theta. But sine theta is an odd function. The sine of minus theta is minus the sine of theta. So I can add these two together. I can add them. These cancel, and I get cosine theta is equal to e to the I theta plus e to the minus I theta over 2. So there's a way of writing cosine theta in terms of exponential. If I subtract them, then the cosines cancel, and I get 2i sine theta. Or I get sine theta is equal to e to the I theta minus e to the minus I theta over 2i. So that's something that we're going to use. And I want you to notice something, that the e to the I theta is oscillating. They oscillate with sines and cosines. So all of a sudden, once I get to, remember I told you that if alpha were complex, then you're going to get roots that have real and imaginary parts. As soon as there's an imaginary part, we're introducing oscillations. So if you get a D that has only real coefficients, but it has complex roots, then what that means is when you invert, even if they're all distinct roots, and you get things that look like e to the alpha it, you could have a step function input and the output oscillates. So that's a new concept. Step function input and the output oscillates. We'll go into that in more detail next time. Today is Wednesday, right? Monday, I think, is a holiday, correct? Okay, I'm with you now. So we're having a test a week from today.